Section 2.3, Containerizing Applications with Docker. The catalog service application is working. Before deploying it to the cloud, however, you should containerize it. Why? Containers provide isolation from the surrounding environment, and they're equipped with all the dependencies required by the application to run. In our case, most of the dependencies are managed by Gradle and are packaged together with the application, jar artifact. But the Java runtime is not included. Without a container, you would have to install the Java runtime on any machine where you want to deploy the application. Containerizing the application means it will be self-contained and portable across any cloud environment. With containers, you can manage all applications in a standard way, no matter the language or framework used to implement them. The Open Container Initiative, OCI, a Linux Foundation project, defines industry standards for working with containers, opencontainers.org. In particular, the OCI image specification defines how to build container images. The OCI runtime specification defines how to run those container images, and the OCI distribution specification defines how to distribute them. The tool we'll use to work with containers is Docker, docker.com, which is compliant with the OCI specifications. Docker is an open-source platform that provides the ability to package and run an application in a loosely isolated environment called a container, docs.docker.com. Docker is also the name of the company behind this technology, which is a founding member of the OCI. The same term is used in several of their commercial products too. Whenever I write Docker, unless specified otherwise, I am referring to the open-source platform we'll use to build and run containers. Before moving on, follow the instructions in Section A.2 of Appendix A to install and configure Docker in your development environment. Section 2.3.1, Introducing Docker, Images and Containers. When you install the Docker platform on your machine, you get the Docker Engine package characterized by a client-server architecture. The Docker server contains the Docker daemon, a background process responsible for creating and managing Docker objects like images, containers, volumes, and networks. The machine where the Docker server runs is called the Docker host. Each machine where you want to run containers should be a Docker host, so it should have a Docker daemon running. The portability of containers is made possible by the daemon process itself. The Docker daemon exposes an API you can use to send instructions, such as to run a container or create a volume. The Docker client talks to the daemon through that API. The client is command line based and can be used to interact with the Docker daemon either through scripting, for example Docker Compose, or through the Docker CLI directly. Besides the client and server components characterizing the Docker engine, another essential element of the platform is a container registry, which has a similar function to a Maven repository. While Maven repositories are used to host and distribute Java libraries, container registries do the same for container images, and they follow the OCI distribution specification. We distinguish between public and private registries. The Docker company provides a public registry called Docker Hub, hub.docker.com, which is configured by default with your local Docker installation and hosts images for many popular open-source projects like Ubuntu, PostgreSQL, and OpenJDK. Based on the architecture description included in the Docker documentation, docs.docker.com, Figure 2.7 shows how the Docker client, Docker server, and container registry interact.
Figure 2.7. The Docker engine has a client-server architecture, and it interacts with a registry.
The Docker daemon manages different objects. For now, we'll focus on images and containers. A container image, or simply an image, is a lightweight executable package that includes everything needed to run the application inside. The Docker image format is the most used one for creating container images, and it has been standardized by the OCI project in the OCI image specification. OCI images can be created from scratch by defining instructions in a Docker file, a text-based file containing all the steps to generate the image. Usually, images are created based on another image. For example, you might build an image based on the OpenJDK one, on top of which you can add a Java application. After it's created, the image can be pushed to a container registry like Docker Hub. A base name and a tag identify each image, where the tag is usually the version number. For example, the Ubuntu image for version 22.04 is called Ubuntu 22.04. A colon separates the base name and version. A container is a runnable instance of a container image. You can manage the container lifecycle from the Docker CLI or Docker Compose. You can start, stop, update, and delete containers. Containers are defined by the image on which they are based and the configuration provided at startup time. For example, environment variables used to customize the container. By default, containers are isolated from each other and the host machine, but you can make them expose services to the outside world through specific ports with a process called port forwarding or port mapping. Containers can have any name. If you don't specify one, the Docker server will assign a random one, like Bazinga_Schrodinger. To run OCI images as containers, you'll need Docker or any other container runtime compatible with the OCI specifications. When you want to run a new container, you can use the Docker CLI to interact with the Docker daemon, which checks whether the specified image is already present on the local server. If not, it will find the image on a registry, download it, and then use it to run a container. The workflow, again, is shown in Figure 2.7. Docker on macOS and Windows. How does it work? In the previous chapter, you learned that containers share the same operating system kernel and rely on Linux features such as namespaces and C groups. We'll use Docker to run Spring Boot applications in Linux containers, but how is Docker supposed to work on a Mac OS or Windows machine? When you install Docker on a Linux operating system, you get the full Docker engine on your Linux host. However, if you install either Docker Desktop for Mac or Docker Desktop for Windows, only the Docker client is installed on your Mac OS/Windows host. Under the hood, a lightweight virtual machine is configured with Linux, and the Docker server component is installed on that machine. As a user, you will get almost the same experience as on a Linux machine. You will hardly notice any difference. But in reality, whenever you use the Docker CLI to perform operations, you are actually interacting with a Docker server on a different machine, the virtual machine running Linux. You can verify this yourself by starting Docker and running the Docker version command. You'll notice that the Docker client is running on a Darwin/AMD64 architecture on Mac OS or on Windows/AMD64 on Windows, while the Docker server is running on Linux/AMD64.
See this code?
Docker provides support for architectures other than AMD64. For example, if you use a MacBook with Apple Silicon, ARM-based chips, you'll find your Docker client running on a Darwin/ARM64 architecture and the Docker server on Linux/ARM64. Section 2.3.2, running a Spring application as a container. Let's go back to Catalog Service and see how you can run it as a container. There are different ways to achieve that, but here you will use the out-of-the-box integration of Spring Boot with cloud-native build packs, buildpacks.io, a project initiated by Heroku and Pivotal, and now hosted by the CNCF. It provides a high-level abstraction for automatically transforming application source code into container images instead of using a low-level Docker file. The Paquito build packs, an implementation of the cloud-native build pack specification, are fully integrated with the Spring Boot plugin, both for Gradle and Maven. This means that you can containerize your Spring Boot applications without downloading any additional tools, providing any extra dependencies, or writing a Docker file. Chapter 6 will describe how the Cloud-Native Build Packs project works and how you can configure it to containerize your Spring Boot applications. For now, I'll give you a little preview of its features. Open a terminal window, navigate to the root folder of your Catalog Service project, Catalog Service, and run the boot build image Gradle task. That's all you need to do to package your application as a container image, using Cloud-Native Build Packs under the hood.
See this code?
Warning. As I write this, the Paquito project is working on adding support for ARM64 images. You can follow the feature's progress on the Paquito Build Packs project on GitHub. See this link. Until that's complete, you can still use build packs to build containers and run them via Docker Desktop on Apple Silicon computers, but the build process and the application startup phase will be slower than usual. Until official support is added, you can alternatively use the following command, which points to an experimental version of Paquito build packs with ARM64 support. Be aware that it's experimental and not ready for production. For more information, you can refer to the documentation on GitHub. See this link. The first time you run the task, it will take a minute to download the packages used by build packs to create the container image. The second time, it will take only a few seconds. The resulting image will be named catalog-service:0.0.1-snapshot by default, project name: version. You can run the following command to get the details of the newly created image.
See this code?
Note: you might have noticed in the previous command's output that it looks like the image was created 42 years ago. That's a convention used by cloud-native build packs to achieve reproducible builds. Subsequent execution of the build command should give the same output if nothing is changed in the input. Using an accurate creation timestamp would make that impossible, so cloud-native build packs uses a conventional timestamp, January 1st, 1980. The last thing to do is run the image and verify that the containerized application is working correctly. Open a terminal window and run the following command.
See this code?
Warning: if you're running the container on an Apple Silicon computer, the previous command might return a message like, "Warning, the requested images platform, Linux/AMD64, does not match the detected host platform, Linux/ARM64/V8, and no specific platform was requested." In that case, you'll need to include an additional argument to the preceding command before the image name, until support for ARM64 is added to Paquito build packs, --platform Linux/AMD64. You can refer to Figure 2.8 for a description of the command.
Figure 2.8. The Docker command to start a containerized application from an image.
Open a browser window, navigate to localhost 8080, and verify that you still get the same greeting you got earlier.
See this code?
When you are done, stop the container with Control-C. In Chapter 6, you'll learn more about how Docker works, how container images are built from a Spring Boot application, and how to use a container registry. I'll also show you how to use Docker Compose to manage containers instead of using the Docker CLI.